Functions are the central object of investigation in most fields of mathematics. In this video, we introduce the concept of a function by definitions illustrated with examples. First, we need to consider the concept of a relation. A relation is any set of ordered pairs. The domain of a relation is the set of first coordinates of the ordered pairs in the relation. The range of a relation is the set of second coordinates of the ordered pairs in the relation. Let's look at two preliminary examples. The set R1, consisting of ordered pairs 1, 2, 1, 3, 2, 3, and 4, 5, is a relation with domain D equal 1, the elements 1, 2, 4, and the range R equal the set of elements 2, 3, and 5. The set R2 equaling the ordered pairs A, 2, B, 3, C, 3, and D, 5 is a relation with domain D equal the set of first coordinates A, B, C, D, and range R equal the set of second coordinates 2, 3, and 5. Now we're ready to define a function. A function is a relation in which no first coordinate is repeated. Let's return to our previous two examples. The set R1 with ordered pairs 1, 2, 1, 3, 2, 3, and 4, 5 is a relation but not a function because 1 is repeated as a first coordinate. The set R2 consisting of the ordered pairs A2, B3, C3, and D5 is a function because no first coordinate is repeated in the set. Now let's consider how functions are related to equations and graphs. We've defined a function as a particular set of ordered pairs. However, listing ordered pairs is not the only way we can express functions. In algebra classes, we usually denote functions by equations and/or graphs. For example, consider that the equation y equals negative 2x plus 6 represents ordered pairs of the form xy. Recall that the graph of an equation essentially identifies all ordered pairs of the form x, y that satisfy the equation. Our equation is a line with slope m equal negative 2 and y-intercept 0, 6. We plot the y-intercept. We move down 2 and right 1 unit to get another point on the line. Then draw the line. This represents all ordered pairs defined by the equation y equal negative 2x plus 6. Let's think about how to find the domain and range of a relation or function that is defined by a graph. For our first example, let's consider the relation given by the 4 points shown. The domain consists of the first coordinates of the ordered pairs in the relation. Thus, the domain is the set -1, 0, 1, and 4. The range is the set of second coordinates used in the relation. Thus, the range is the set consisting of the elements -3, -2, 2, and 3. Remember that in specifying sets, the order of the elements listed inside the braces is irrelevant. Let's consider a second example in which the relation is defined by a graph. Suppose that the relation is defined by the points on the given ellipse. We can find the domain and range by considering which x-coordinates and y-coordinates, respectively, are used in the graph of the ellipse. Remembering that the relation is defined by the points on the ellipse, the domain is the interval of x values used in the graph. This is the closed interval from -4 to 4. Similarly, the range is the interval of y values used in the graph. This is the closed interval from -6 to 6. Let's consider a third example. Suppose the relation is given by the points on the line y equal -2x plus 3. To find the domain of this relation, we need to consider the set of x values for which the line exists. Since the line exists for all real values of x, the domain is the interval from -infinity to infinity. Similarly, the range is the set of all y values used in the graph. Thus, the range is also the interval from -infinity to infinity. When a relation or function is defined by a formula, we need to agree on how to define the domain. We use the domain implied by the existence of the formula. Unless otherwise stated, when a relation is specified by a formula, the domain of the relation is assumed to be the set of all real numbers for which the formula expression is defined. Let's consider two quick examples. The domain of y equal 1 over x is the set of all real numbers x not equal to 0, because all non-zero values of x can be substituted into the formula. The domain of y equal the square root of the quantity x plus 2 is the set of all real numbers x greater than or equal to -2, because these values make the radicand non-negative. The vertical line test is a test for when a graph is the graph of a function. We often abbreviate vertical line test with the initials VLT. If every vertical line intersects a graph in at most one point, then the graph is a graph of a function. Let's consider the same three examples from earlier. First, consider the relation consisting of the 4 points -1, 3, 0, -2, 1, 2, and 4, -3. We draw some sample vertical lines to see if any of them intersect the graph more than once. Using the vertical line test, we conclude that the relation is a function. Our second example is the relation defined by the given ellipse. We draw a variety of vertical lines and notice that some of them intersect the graph more than once. Therefore, the relation defined by this graph is not a function. Finally, consider the relation defined by the graph of the line y equals -2 plus 3. We draw some sample vertical lines and see that none of them will intersect the given line more than once. Thus, the relation defined by y equal -2x plus 3 is a function. This video defined the notion of a function. The next video will discuss how functions are expressed and evaluated.